Let's quickly look at this question, which is often used as an illustration on trigonometric substitution and integration by parts in a particular or in a generic integral calculus course. All right, so let's see. If you are to use trigonometric substitution, and if we have something like a squared plus x squared in the integrand, somewhere in the integrand, then the most obvious substitution would be theta equals tan inverse x over a. So in this case, the substitution we're going to use is theta equals tan inverse of x, because a equals 1. Obviously here, a should be taken to be greater than 0. Alright? Now, theta equals tan inverse of x. This gives us a lot of things. Some of those things are x equals tan theta, theta being between minus pi by 2 and pi by 2, and the derivative of x with respect to theta being sec squared theta. Okay, now this will create a lot of problems as we shall proceed, but for now let's use this substitution and obtain this integral as sine inverse 2 tan theta plus 1 plus x is again tan theta, so tan squared theta, and we need to change the variable of integration from x to theta, so we're going to use some substitution factor. And as we know, if we have an integral of the form hx dx and we're making the substitution u equals gx, then we need to change the variable from x to u. But if we do this, we need to introduce the substitution factor, which is 1 over g dash of x. And obviously we're going to need to express everything in terms of u, because the variable of integration is now u. Okay, that's it. And since we have that this g dash x is definitely du over dx, and in our case it is d theta over dx, something like this. But inverse circular function, this represents an invertible function, so 1 over d theta over dx can be rewritten as dx over d theta. Okay, so the substitution factor is simply dx over d theta, which is equal to sec squared theta. So sec squared theta like this. Next, after all this, let's try and simplify this thing, which is the argument of the inverse sine function. Twice tan theta over 1 plus tan squared theta. This is equal to twice tan theta over 1 plus tan squared means sec squared, 2 times sine over cos, and this is cos squared. All right, these get cancelled out. Choose sine theta cos theta means sine twice theta. Sine twice theta. So all I can do is write it as sine inverse of sine of twice theta and sec squared theta as it is d theta. No problem till now. So far, so good. Okay? But one of the major mistakes or misconceptions is that most people solve it like this, but they forget that we can write as this only if this is between minus pi over 2 to pi over 2. But do we have this condition? Let's see. Do we have this condition? Do we have this condition? We had minus pi over 2 to pi over 2. Theta lies between them. Minus pi over 2 and pi over 2. So obviously theta lies between, oh my god, twice theta lies between minus pi and pi. Wait a minute. Okay, so where was I? Right. Twice theta can be between minus pi and pi. So it's a problem because let's say pi is somewhere over here, pi over 2 is somewhere over here, minus pi over 2 will be somewhere over here, and minus pi will be somewhere over here. As long as twice theta is between these two values, as long as twice theta is over here, it is okay to write that thing over there. But if it is within this part, be careful. I'm talking about twice theta, not theta. Not theta, twice theta. Because the argument inside the inverse sine function involves twice theta. Twice theta can be between pi by 2 and pi. Twice theta can also be between minus pi by 2 and minus pi. Okay? So we need to consider two more cases. We need to consider two more cases apart from this case. Okay? So what can we do? We can write as long as twice theta is between minus pi by 2 and pi by 2, we can write this as integration of twice theta sec squared theta d theta, as long as minus pi by 2 and pi by 2 twice theta is between minus pi by 2 and pi by 2. Alright? As long as this condition holds. What if this condition does not hold? What if this condition does not hold? Okay. What if this condition does not hold? What if we have pi by 2 to be between twice theta, sorry, to be between pi by 2 and pi? Well, one thing what we can do is revert the signs and write it something like this. Now, if we add pi to each term, we're going to get 0, pi minus twice theta, and pi over 2. All right. Now, let's see. Sine of pi minus twice theta is equal to sine of twice theta, right? Sine of twice theta. So, sine inverse of sine of pi minus twice theta will be equal to sine inverse of sine of twice theta. Okay? Sine of twice theta. And since this thing over here is between 0 and pi by 2, let's see, pi minus twice theta, right? Here's 0, here's pi over 2, between these two values, pi minus twice theta, so it is between minus pi by 2 and pi by 2, so it's okay to take sine inverse sine of this thing as pi minus twice theta. So what do we get is that under this condition, sine inverse of sine twice theta is equal to pi minus twice theta. This thing is equal to pi minus twice theta sec squared theta d theta. Under this condition, okay? All right. Now, what if we have this condition? What if we have this condition? Okay, we're obviously gonna have sec square theta d theta because that won't change. Only the value of this thing will change. Okay, this thing will give this, and we'll give something over here. Now let's look at this condition, the other condition, minus pi twice theta minus pi over 2. Now if we add pi to each term, we'll get something like this. Now let's see. Sine of pi plus twice theta will be equal to minus sine of twice theta, right? So if we take the sine inverse on both sides like this, then what we can do is that we know sine inverse of minus whatever that we have inside, as long as x has a valid value, okay, as long as this value is permissible or admissible or whatever you want to call it, we can write it like this. As long as x is between input, right? Yeah, minus 1 to 1. And then we can write it like this. So this is equal to minus sine inverse of sine twice theta. And since this is between 0 and pi by 2, we can write pi plus twice theta to be equal to minus sine of this. So sine inverse sine twice theta is equal to minus pi plus twice theta in this case. In this case means minus pi less than twice theta less than pi by minus pi by 2. Okay, this is it. This is all. Now we have considered all the possible cases. So now we are not really interested in the cases involving twice theta because the original variable of integration is x. So let's try and write it down in terms of x. All right. Okay. First of all, minus pi over 2 twice theta. Pi over 2 means theta is between these two values. Okay. Theta is between these two values, but theta is equal to tan inverse of x. Tan inverse of x means here's pi by 2. Sorry, minus pi by 2. Here's pi by 2, positive x, negative x, positive y, negative y. And increasing and asymptote, whatever. Minus pi over 4 to theta. Okay. Oh, sorry. Yeah. We need the values of x's over here. Pi over 4. Theta is between pi over 4 and minus pi over 4. Like this. And we know that this corresponds to the point 1. This corresponds to the point. This corresponds to the point minus 1. So this interval corresponds to this interval, and so this condition reduces to this condition reduces to x being between minus 1 and 1. So this is the case, minus 1 less or equal to x less or equal to 1. Okay, now this will reduce to pi by 4 being less than theta being less than pi over 2. So above this means greater than 1. So this works for the case x being greater than 1. And minus, this means minus pi over 2 less than theta less than minus pi over 4 less than minus pi over 4, and between these two values this will mean somewhere over here, so less than, x is less than minus 1. So this corresponds to the case x less than minus 1, like this. Okay, like this. So we've gotten the 3 different representations for our integral. Now let's just simplify this part of the integral. This can be written as pi minus twice theta, right? So integration of pi sec squared theta d theta minus, so this pi gets out of here, and this is twice integration of theta sec squared d theta. Or let me just simply include twice theta over here. I'm going to integrate twice theta. Nobody's going to bother with that. And similarly, this is minus pi plus twice theta. So this is minus minus pi sec squared theta d theta plus integration of twice theta sec squared theta d theta. Okay, these are the cases. Now let's integrate this thing over here. Let's integrate this thing. First of all, integration of twice theta sec squared theta d theta. Basic ILATE rule, as long as it is applicable. A means twice theta and T means sec squared theta. So first function times the integral of an antiderivative, okay, antiderivative of the second function minus the integral of the derivative of first function, times the integral of the second, okay, integral of the second function, okay. This is equal to twice theta, tan theta as it is, minus twice log of, what do we have? Log of secant of x. Sorry, secant of theta. All right. This will be equal to something like, okay, this is how it works. Take u, the derivative of u will be sine theta, so this is the what do you call it? The substitution factor. Sine gets cancelled out, minus 1 by u, integral du, log u, but minus log of, what do you have here is u, means cosine of x, but negative, plus c obviously, which gives log of secant of x plus c. This is how it works, okay. So this part of the integral is something like this. Now twice tan theta means x, and theta itself is tan inverse of x, minus twice log. Now let me just write it as sec squared theta plus c, okay, because that will be easier. Sec squared theta means 1 plus tan squared theta. And this will simply mean 1 plus tan squared theta would simply mean 1 plus x squared. So this is equal to twice x tan inverse x minus log of 1 plus x squared plus c. All right. That's how it works. That's how this thing works. Now let me quickly check the answer. Let me look at the answer key, all right? Yeah, this is correct. So I've completed one of the parts. The first part is obviously this, okay? First part is twice x tan inverse x minus log of 1 plus x squared. Now, since the argument of the logarithmic function is positive, I'm not including the modulus sign. All right, plus c. When? For something like this. Next, I'm going to use this directly. I'm not going to integrate it again because this will be the same thing again. All right. So I'm not going to do it again. Just for the completion, sec squared theta d theta means pi tan theta. I'm not going to use plus c because I'm going to use an antiderivative of this thing and then an antiderivative of this thing plus c. Okay, this is an antiderivative of this thing. Okay, pi tan theta, and by tan theta I mean x. Okay, by tan theta I mean x. So this is basically pi x minus the antiderivative of this thing, twice x tan inverse of x plus logarithm of 1 plus x squared plus c. And this will be for x being greater than 1. Now finally finally, finally, for this part, this is going to be something like minus pi x, okay, minus pi x, and minus of this thing means minus of this thing twice x, tan inverse of x, okay, minus of this thing plus log of 1 plus x squared plus c for x being less than minus 1. All right, so we've covered the entire domain of tangent, inverse tangent function, okay, for all real values between 1 and minus 1 and greater than 1 and less than 1. We've covered the entire domain, and this is what the antiderivative or the indefinite integral should look like. Now, if we are given this condition, these two are not necessary, but if we aren't specified with any kind of a restriction, then we must consider each and every possible case, which will lead us to these kind of things. Okay, so while using trig subs, you must be really careful that you understand the properties of the inverse circular functions or inverse trigonometric functions. Otherwise, you're going to be in a lot of trouble. You're going to get into trouble. Okay? All right. That's it for today. Thank you very much.